quantum neural networks await us on the horizon, and our next speaker is a distinguished expert in the field. Please join me in welcoming Professor Antoine Jacquier from Imperial College London, who will enlighten us on quantum neural networks and their applications.
Thank you very much. Okay, that's the timing thing. So, I want to talk about quantum neural networks and applications. So I'm not an expert in quantum, and I'm not an expert in neural networks, even less. But what I'm interested in and what I actually find exciting is the interplay between the two parts. So I'm based in the math department, so the talk is a bit more on the theoretical side. And I think this interplay, that's actually what I like about it, because it's kind of a big umbrella under which we can do some exciting interdisciplinary science. And next, yes. So interdisciplinarity, I've been in academia for a few years now. I always hear about that. Very often, those are kind of not very nice keywords, but not very well done in practice. So at least this is a very good umbrella where, so this research is done jointly with different departments in Imperial, funded by several grants in the UK. So basically most of it is done jointly with obviously people from physics and computer science, but also people from aeronautics. This is on the academic side, and on the industry side, so we also have collaboration. We'll hear quite a few talks, I think, tomorrow by people from Rigetti. So we have a project with them, and by people from Standard Chartered as well. So it's really interdisciplinary. But the talk itself, what I want to go through, think of it as a short crash course on quantum neural networks. And so crash course with a few new things and a few quick view on why we might care, well, let's say why I care at least, but why we might care about quantum neural networks in the future. So this picture, I think most people might have seen it in one way or another. This is a classical neural network, classical feed-forward neural network, where, so this is the left part. So on the left side, you have your inputs, and then it goes through several layers and nodes with some nonlinearity, and you have your output at the end. Right? This is the most standard classical neural network we've seen. If I change it a bit, if I abstract it a little bit, so this is my picture. In some sense, I did say I'm not a machine learning expert. Right? I have the input, I have some big box in the middle, and the output on the other end. I don't call it a black box because we actually know exactly what it is, right? So let's call it a gray box. Quite transparent, but gray box. So let's modify it a little bit, right? So X is the input, Y is the output. So X is, I call it my initial system. There's no quantum here, right? Then I have a layer which encodes this data, this X, that somehow puts it into the network. Then I call this box, maybe B would be a better name, but M for the machine, which takes as parameters or input this encoded data X, and then output something, the Y. And then, so this is a ruler, right? So this, of course, will mimic the measurement, but for now, this is just the way I view my output data, whether I view all of it or part of it or whether I transform it, but this is the way I measure, if you want, but not in a quantum sense, the way I view my output data. And, okay, so I can call S my system. My system starts in the 0 position, just initial position. I encode it, so now it's X, and I transform it, it becomes Y at the end. And now, the difference between this slide and this slide is now this is quantum, where here everything was classical, so I don't have any quantum state, I don't have any quantum gates, but now my initial system, I call it cat 0, right? So these are qubits initialized. I encode my data X into the system. Of course, there's a lot of work there. Every step there's a lot of work, but I managed to encode my data into the system. I transform my data with this big gray box. So of course now this gray box has to satisfy the rules of quantum mechanics, right? So these are just unitary gates. And then it becomes quantum state Y. And then I may or may not, depending on what the problem is, I may or may not measure it. Of course, I can add a layer, which is I can parameterize my gray box in the middle. So it's not only driven by the data X, but by some, if you like classical neural networks, there would be your classical hyperparameters. Here, theta would be the rotation, rotation angles of all the quantum gates you're using. Right? But in some sense, these are just same as hyperparameters. Okay, so these few slides is really just to emphasize that at least at this level, this quantum neural network is really the same as a classical feed-forward neural network, or at least the same in this sense here, but of course the details are very different, right? And in fact, this is what this big gray box usually looks like. This one doesn't mean anything in particular, right? But this is just, I start with my initial system in state 0. I encode my data in some sense. Then I have layers, so the vertical blue lines kind of mimics the idea of layers of classical neural network. I have layers of gates, so some with, does it work? No, there's no pointer, but there's no. So theta 1, theta 2, theta, and so on are my hyperparameters, so my rotation angles, and then I have controlled gates as well, and so on. And I have the output, which is the state at the end, before measurement. Right. So this is usually a parameterized quantum circuit, which is the usual terminology. Some people would call it quantum neural network, but this is exactly the same. Of course, when you measure many times, right? So similarly to Monte Carlo types, so the output will be a probability distribution, right? Discrete probability distribution over the quantum states, right? Which are labeled. So say I have two qubits. So my labels are 0, 0, 0, 1, 1, 0, 1, 1. You run your big circuit, and you have a discrete probability distribution over 4 points, right, where the labels are just the quantum states. I can associate the label, each label, to some event or some features that I want to describe, but this is the output. So this is kind of the classical setup. Right? The output here is a probability distribution. Of course, we may not only care about probability distribution, but this is just the starting point. So just one word about the data encoding. This is in general very hard to encode classical data into a quantum computer. And I want to emphasize that I hate the term quantum finance, because in my view there's nothing quantum about finance, right? Financial data are time series, are features, are many things, but we're not looking at quantum data. Right? We're looking at classical data, and we use quantum computing for finance. So we need a way of encoding this classical data into a quantum computer. So the simplest way, and for now I would say the most useful way, is to encode it through rotation angles. So I would, let's say you have features, x1, xn, and I would encode this data, let's say normalized between 0 and pi, or 0 and 2 pi. I would encode them, each of them, into each qubit through rotation. Of course, it means as soon as I do this, then my circuit is not linear in the data, right? Because it appears in the angle, which is actually a nice feature, because remember, classical neural networks are not, the whole point is to have some nonlinearities. But that is inherently given in this encoding. Of course, this is very simple. I can only have 1 qubit per feature, but of course I can add layers of qubits. So sorry, these should be x. The theta should be x here, so I can add several layers of encoding the features. So once I have a neural network, or quantum neural network, I can try to do classical training, the way I would do training for a classical neural network. So the simplest way, it's funny, it appears, I should have nice brackets somehow. Maybe it's the PDF that appears funny. So my matrix, or my vector of hyperparameters of rotation angles, are all these theta. When I look at classical neural networks, of course, I want to minimize something. Something is a cost function, so I can define a simple cost function. So I apologize. Somehow the PDF, there should be a sum, right? So L of theta is 1/2 of a sum. This is the sum over the data I observe and the output of the quantum circuit, right? This is just an L2 loss function. And the classical way, so here there's one thing, this is the Fk of theta, is the output of the quantum circuit after measurement. So that this loss function is calculated in a purely classical way. So this is kind of the hybrid classical quantum system where the data is generated via a quantum circuit, via a parameterized quantum circuit, but measured, and the minimization itself is done at the classical level. And then you will loop over this. Of course, looping over this, meaning you need to change all the rotation angles, which may or may not always be feasible because of the hardware. You cannot have any rotation angles. I think right now, maybe this is a bit better now, but the size of the increments, so the size of the rotation angles, you can not go as small as you want. So there are hardware conservations, right? I'm not talking about the hardware here, but of course there are hardware conservations. And all the algorithms I'm talking about here are completely hardware agnostic, right? Of course they should be, or they could be tailored for specific hardware. Now, how good is a quantum neural network? A parameterized quantum circuit. So in the classical case, people have been using classical neural network for a very long time, but it's somehow fairly recent that we have solid theoretical foundations that give us more information about how many layers do I need, how many nodes do I need to be able to express any function or any distribution I want. So the background, so this usually falls into the class of what's called universal approximation theorems, which are basically saying if I have a function, one dimension or many dimensions, how close can a classical neural network approximate this function in terms of number of layers, number of nodes, and so on. And there's been a lot of research. There's a lot has been done also very recently, and is still very active, either as general convergence result or something more precise with bounds. This is in the classical case. Of course, you can ask exactly the same question in the quantum case, and there has been a few results. So as you can see, 2021. So this is more recent, and so this is what we've been focusing on in the past year. Okay, so this is bad. I don't know why it appears like this. Okay, so I apologize for this. PDF was working fine on my computer, but so anyway, I can tell you the story without the formula. It's maybe even better. What it says is, so there are two parts. What we prove. So this is John with Lucas Gonnen, who's a colleague in Imperial in the math department, and basically it says, on the one hand, it's an existence result, which is if take a function, any function in any dimension in Rn, I can construct a quantum circuit that will approximate it and the error of this approximation, the L2 error, will be 1 over square root of n. Will be bounded by 1 over square root of n. Think of n as the number of qubits, so when I increase the number of qubits, the error will tend to 0, but we have a precise error bound for it. So it's nice because it gives you a theoretical guarantee that as you increase the number of qubits, your approximation will be better and better. Now, there are two things. First, that's a nice theoretical result, but it may not be very useful. So the second part of the result is actually we show how to construct this function. Let's see if that is a little bit better. That is not better. Okay. They'll try to fix it, but in worst case, I'll tell you the story. That's fine. Oh, this is cool like this, right? Okay. Thank you very much. Okay, so that's the result I mentioned, right? I have a function f, which is my target function, and I can construct a function f n theta r. So theta are my vector parameters, n is the number of qubits, and in the L2 sense, so mu is any measure, but just think of Lebesgue measure, so mu of dx is just dx. So the L2 approximation is bounded by 1 over square root of n, and this L1 is just a constant. So now, of course, this is an existence result. Can we actually construct this approximation? The answer is yes. So the circuit looks like this, V and U. Okay, this is not very useful. If we want a little bit of detail, but I don't want to spend too much time on the detail. Well, first, so this function f, this is the, I know, that's the one. This function f is, if you remember at the beginning, we said the output of a quantum circuit is a probability distribution. Here, f is a function, so I can't necessarily view it as a probability distribution, but in fact, I can compute the function f through measurement. So in fact, the function f of x, will be given in terms of the output probability distribution. So that's another way of encoding values, not just as probability distribution, but if you want to encode value as functions, you can do that through the probability distribution that is generated by the quantum circuit. And in fact, we have a constructive way to construct this probability distribution. So we can, from a theoretical point of view, we can construct the unitary operator in the quantum state that would correspond. There's still a bit of work which is not there to actually construct the quantum circuit, meaning to convert the quantum state we have into a state being able to actually construct it, right? And there's a lot of work right now saying can I construct any quantum state, and this is not an easy statement. Here, the quantum state we have has some particular feature, so I think it's possible, but this is not completely finished yet. So this is universal approximation for a quantum neural network. We can add one layer, which is this concept of quantum reservoir computing, which is the quantum analog to classical reservoir neural network. And the idea is what? The idea is, because the classical neural network, I have all these parameters, hyperparameter theta. That's a big space to optimize over, to minimize over. So what I'm going to do is I'm going to sample all this theta from some distribution. And then I'm just going to add one layer over which I'm going to optimize over. And the idea is this one you can call it a gray box, where you sample all your parameters from, will generate a space big enough, and then basically I just do a linear regression onto the final layer. So this is the concept of reservoir computing. Of course, it's much faster because this is just a linear regression at the end. And you can do the same for the parameterized quantum circuit. So this is what we do here. So this is basically the same result, saying, oh, I can construct a quantum reservoir neural network that will approximate any function with a precise error bound of the form 1 over root n. And we have, again, a very specific way of building it. I'm not going through the details here. One thing I want to emphasize is that this bound does not depend on the dimension of the function. There's a very similar result in for classical neural networks. Actually, these results in the classical setting were written by MacArthur, Lucas Gonnen, so we kind of recycle what they did in the classical case. So it's not that surprising, but it's dimension independent. So in terms of applications, so I listed 2 applications, but I really only want to go through one quickly, which is quantum for PDEs. I left the other one on the slide just because the slides might be distributed, so in case you're interested, we can have a look, but I won't talk about them. So quantum for PDEs, which is, I want to solve a PDE, and ideally a high-dimensional PDE. Can I use quantum neural network to solve PDEs? So this is done with people from aeronautics, where they're interested in PDEs that arise in fluid mechanics for turbulent flows. But the general setup is I have a PDE, LU of x is 0. So L is some differential operator. And I have this in a domain with some boundary condition on E. E is your boundary. And classical neural networks, so I construct an approximation for the function, a neural network that will approximate the function, and my loss function is just the distance between the sample I have for the function and what I construct with the neural network, and I minimize over this. This is the classical way, or classical neural network approach to do this. Now there's the PIN approach, the physics-inspired neural network approach, which is similar, but basically generate samples of the data, both in the space you're considering and on the boundary, and look at 2 parts, basically the equation evaluated for the neural network function, the function that you generate via neural network, and the loss function on the boundary. And in fact, because this is the classical case where the function is generated by a neural network, you could ask whether you could do the same with a quantum neural network. Basically, instead of writing a neural network to approximate the function, you would approximate the function via a quantum neural network. And at least because we have theoretical guarantees that the quantum neural network will converge to the function we're interested in, there's hope that it would work. So I just have some quick numerical examples. So for the P-Laplace equation, the heat equation, some simple Hamilton-Jacobi equation, that basically, I don't want to go through it. No, basically, it says that it works pretty well, at least in dimension 2, 3, and we're working on higher dimension, which are, of course, the interesting thing. The one thing I want to mention there is how do you actually construct this function, this approximation function? Stefan mentioned that a little bit at some point, which is the way you evaluate the function is as an expectation, as a quantum expectation. So I have some details about that, but I will skip it just for the sake of time. Okay, so that's the numerical example. So that actually, even with 6 qubits, you can actually solve things, at least in dimension 2 or 3. It seems to work pretty well, but we still need to push the analysis further. There's another example, quantum GAN, which I will skip altogether. So I'll put some details, but I'm not going to go through this. So the takeaway message here is, I said I'm not a quantum person, but I think there's a need, maybe it's a personal bias, there's a need for more math in there to understand more theoretical foundations, solid foundations, such as these universal approximation theorems for quantum circuits. So this is only for quantum neural networks, but similar statement could be made for quantum optimization, for example, and to some extent for quantum simulation. So say quantum computing for simulation, but not quantum simulation. And so there's a tiny bit of advertising because Alexei is here and a co-organizer. So we wrote a book on quantum machine learning and optimization in finance. So with Alexei Kondratiev here. And so that concludes my talk. But if you allow me, I have one announcement to make, which is, so as I said, I'm in the math department in the academic math finance community. And so finance and stochastics is one of the leading, has been for a long time and still is one of the leading journals in the field. So this is really a math journal, and finance and stochastics. But it's opening to new, it's open to new areas and looking forward to new contributions, especially on the mathematical side for quantum computing in finance. So there will be a special issue. So I will be a guest editor together with Josef Teichmann, who's somewhere in the audience. He's easy to spot. He's the one with the flower shirt usually. And so the plan for publishing will be next year. So submission deadline will be end of the year. So we're happy to look at any contribution. With, of course, it's a math journal, so a strong emphasis on the mathematical properties of the algorithms, convergence properties, and that's it. If you have any questions, of course, feel free to ask, and thank you very much for your attention.
Is that the kind of thing you talk about there, computation, require hardware, special hardware to do?
Of course.
Okay, number one. Okay, that's easy.
I mean, okay, there are two parts. First, there's a theoretical result, right?
Yep.
Which is I can construct,
yep,
theoretically, meaning I can write down a quantum state. I can say there's a unitary matrix that transforms this state into that state, and this, if I do the computation, I will approximate any function. Of course, you know, I can be happy like this, right? But of course, ultimately, you want to implement it. If you want to implement, yes. Of course, this is hardware agnostic, right? So in order to construct this, you know, whether we need, because we have a big unitary, whether you can decompose this big unitary into tensor product or 1 qubit or 2 qubit gates only, this I don't know, right? In theory, yes, but in practice, this is a bit more tricky.
Okay, good. And the second question is very quick. Is that it's really lovely to see that you have universal approximation for quantum, the formula there. But in reality, in many pattern recognition applications or maybe AI machine learning applications, it's not the absolute errors that you care about. It's the structure of the error you care about. Do you have any thought about what kind of structure?
So I have one answer, which is,
please.
In fact, does it work if I do this? No. Well, that's okay. Don't worry. When I wrote this L2 error, I said this is basically f of x minus the approximation, right? And there was a mu dx. Mu is any probability measure, meaning you can focus this probability measure in some areas of the space. It doesn't have to be just dx. It could be, very high in this space because you want a lot more information there, and mu has very low probability in that space. So you can specify any mu that will work. So if you do pattern recognition, you might want to put more emphasis in this corner of the image. So having mu have high mass in that corner and low mass there.
Okay, so in that case, classical computing neural network versus quantum neural network, maybe the universal approximation seem to have same kind of problems, right?
Yes.
Okay. Okay, good. Thank you very much.
Okay, in some part of your talk, you talk about reservoir quantum machine learning, and you included actually one layer after the parameterized part. Do you still need to train the parameterized part, or you just put some random numbers and only focus on the regression part?
Yeah, so that's the idea. The big box in the middle, which I sample from, I sample it once, and that's it. So I don't train it anymore. There's no training. There's only optimization, minimization over the last layer. And here, actually, our last layer is post-measurement. So, but I don't have to train the whole thing in the middle anymore.
And then have you explored the depth of the circuit that you need as a reserve, and the parameterized part that you actually do not train? So how deep it is?
So in our case, so from the initial state to the terminal state, in fact, so the big unitary we have is 4x4 diagonal blocks. So it's actually not too deep. We still need to work a bit to be able to decompose it properly, but it's not too deep because it's really diagonal matrix, this unitary, with 4x4 blocks, and you have nothing off diagonal, meaning you don't need to go too deep outside. Now, to answer precisely, I would need to work it out.
Thank you.
Yeah, I have two questions. They are related. In the back propagation algorithm that you showed, I've noticed you're using the discretized algorithm instead of the continuous gradients. Is there a specific reason that you have to do that? And the second one is related to that, is in the QPen that you showed, in the loss function for the PDE, are you also using the discretized PDE, or are you using the continuous one, and why would you have to resort to the discretized PDE if that was the case?
So for the first question, the idea is a hybrid system, right? So you learn one solution, you build one solution, so you fix the theta, or vector of theta, you build one solution in a quantum way, you measure, so that gives you a classical number, you compare it to your data, and then you do a gradient descent, right? Then you have a new vector of theta, and you redo the quantum, you generate a new solution, quantum solution with this theta. So in some sense, there's no proper back propagation. It means I don't go through the quantum circuit. There's a way of doing it purely quantum way, but this is not very efficient from my understanding. So here it's really just bumping the parameters in a classical way and plugging them back into the quantum computer. Now on the PD side, so the loss function, we discretize it. So we actually sample points randomly, both from the domain we're looking at and from the boundary. But we sample point randomly from this domain, and we discretize the differential operator.
Yeah, probably for the same reason that it's very inefficient.
But actually, no. We have a version where we discretize, but because we assume that our quantum neural network function is given as an expectation, in fact, we can approximate it. We don't need to discretize this. We can compute the gradient and the derivative exactly, actually. So we don't need to discretize. At least in the cases we're looking at, where solutions have some smoothness properties. It may not be true if you have very highly regular functions, but for functions that have some smoothness properties, we can actually write the function as an expectation of another function, meaning that we can actually compute the derivative explicitly. So we don't need to discretize the operator.